test. All right, in Calc 1, that didn't strike fear into the hearts of people everywhere. The idea of a second derivative test. You just take the derivative a second time. But in Calc 3, we know second order partial is like, we want second order partial with respect to x or y or mixed second order partial. Oh, geez, which one do you want? So, very procedural. The issue, though, is it's not a short procedure, right? And not short in actually reading through it and not short in carrying it out. Suppose that f(x,y) is continuous second order partial derivative of some open disk containing the blah, 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 blah. All right, so you have critical values. The continuous second order partial derivatives, that's like a throwaway statement from Calc 1, but here it's so important because what it means is that your second order partials are interchangeable. Right? So partial xy is the same as partial yx, right? Because it's continuous second order partials, right? If it were not the case, then this all falls flat, all right? We define the discriminant, right? So we get our critical values, still got to do that, but we define the discriminant by this formula. Second order partial with respect to x, then y, then the mixed. We'll talk about where that comes from next time. Once we get that value, it's kind of like discriminant sort of from quadratic formula, where you have conditions associated with the type of value that you have. If your d is positive, and so is your second order partial with respect to x, then you have a local minimum at AB. If only the d value is positive, but the second order partial with respect to x is negative, then it's a local max. If you have a negative d, this is the one that you're hoping for, because that means, well, actually these two, kind of. Three is really the one you're hoping for, because it's the one where you could draw a conclusion by doing the least amount of work. Your d value is negative, then that means there's a saddle point. It's neither maximum nor minimum. Critical value doesn't lead to a max or a min. The d equals 0, it depends on the question. If it says use second order partials to draw a conclusion about or classify the critical points, then that's fine. But if your objective is to find the critical points and then find extrema, and you get a d equals 0, there really is nothing more frustrating. Because what that means is, well, maybe it's a max, maybe it's a min, or maybe it's neither. I can't conclude based on what we've done, which means I wasted all my time doing that, which is brutal, right? So definitely something to be avoided. But anyway, let me find my first order partial with respect to x. 4x cubed minus 4y. And my first order partial with respect to y, 4y cubed minus 4x. All right. Now these have to be equal to each other and equal to 0 in order to have a critical value, right? Or if either of them don't exist, but so far continuous differentiable all the way through. So I'm going to set it equal to 0. I'm going to clean it up. I'll make this y equals x cubed. All right, the other one, same general idea, except it's x equals y cubed. All right, so we have a relationship here. That's something. Doesn't seem like an overly meaningful one until, well, this is the geeky math teacher inside of me. Well, inside of me, that's who I am. So it's this and that. So that's the definition of a system of equations. Two equations that are true simultaneously. So I need y to be equal to x cubed at the same time that x is equal to y cubed. If that's the case, that allows me to substitute from one equation into the other. So I can replace, for example, the x cubed here. I'll replace the x with a y cubed and make it y equals y cubed cubed, which means y is equal to y to the 9th. Right? Now, just be careful because Algebra 1 students do this and Calc 3 students do this too. You can't just divide out a y. You're going to lose a solution. All right? So bring over the y. Y to the 9th minus y equals 0. Factor. And solve. You get y equals 0, y to the 8th minus 1 equals 0, which means y to the 8th equals 1, which means y is equal to plus or minus 1. All right, so we have 3 potential y values, which correspond to 3, well, possibly 3 potential unique x values. All right, so x is equal to y cubed. So if x is equal to y cubed, and we have these 3 y values, then we would get ordered pairs. If I plug in a 0, I get a 0. If I plug in a 1, I get a 1. If I plug in a -1, I get a -1. And these would all have z values associated with them. But again, instead of plugging and chugging away, well, the first one I can do. 1. Well, actually, I guess I could do them all, because these are easy numbers to work with. So 2 minus 4 is -2, plus 1 is -1. Two, so same deal?
Yeah, same deal.
Same deal, right? All right, now it's hard to see this diagram, but it does look like kind of like a pair of pants, sort of. So it comes down and then it goes up. I'm not going to describe what that area is. And then it comes back down to the other pant leg. And then, so you have what appears to be a couple of minimum values, and then up in that area, that could be a maximum, or it could be a saddle point. So, yeah.
But I'm sorry, what would be the maximum? Or the minimum?
These two.
But without that picture, that's my point. That's like...
That's why we investigate using this approach. Because if you don't have the diagram, then you can't even go by that. So at this point, if that diagram were not there, I'd look at this and say, I have 3 possible coordinates that could represent 3 possible things. Min, max, saddle point. I don't know what's what. All right, so what we do is we figure out the discriminant for each one of them. All right. So I need my second order partial with respect to x, which requires me to see my x, 12x squared.
Not give us a number of these problems. You just write way too big. I like font 6. That's all.
Yeah, you just got to dial back your font. I mean, I figure if I spot you the first 100 pages and notes, or you can go to notebook pages every once and again. F of yy, f sub yy, that's going to be 12y squared. So I need, for each of these xy pairings, right, I also need the mixed second order partial. So f x y. So I'll take my x model and do it with respect to y, which is a little bit easier, a lot easier. It's just a -4. So that's nice. All right, so again, I'm going to evaluate each of these for each of the coordinates and see what my d value is. All right, so I'll do it right here. Oh, sorry. So plugging this in for x and y as applicable. All right. So 0 times 0 just trying to be able to point to the formula. So plugging the a, b values into the second order partial with respect to x, it doesn't call for a y, so I only have to plug in the x value. The f of y, oh, that should have been no, it's still a 0, because I'm plugging in a 0 there. But then we're going to subtract the negative 4 squared. So subtract negative 4 to the second power, and that's going to give me a 16.
Minus 16.
Minus 6, negative 16. All right, so then I'll do the same thing for 1, 1. And then we'll do the compare and contrast all in one shot. So 12 times 12. And it's going to be the same deal because the second order partial with respect to y, the mixed partial, is still negative 4. It's constant. So we're still going to have a subtraction of 16. So 144 minus 16 is what, 128? And then I do the same thing for -1, -1, and that's going to give me the same result, right?
Yeah.
All right. So, looking at my conditions, I always go for the saddle point first. All right, saddle point is the easiest one to identify. If your discriminant is negative, then you have a saddle point. All right. So my saddle point is at 0, 0, 1. In the case of the second two coordinates, I have a positive discriminant in both cases. So it's really just going to come down to my second order partial with respect to x and whether it's positive or negative. So I extend upon this and I evaluate my second order partial for 0, 0. Oh, we already did 0, 0, sorry. That's the saddle point. And I wrote 0, 0 again like a fool. Can't get out of my own way sometimes. So that's just a 12. That's greater than 0. So we now know that at 1, 1, -1, what happens when my second order partial is positive? What do my conditions tell me?
Either minimum or maximum, but
It's minimum.
yeah.
Local min. All right. And then when I plug in -1, -1, I get a positive again, right? So it's still a local min. Now the diagram helps, definitely. And you know, I pick and choose my battles when it comes to that. Sometimes I want you to have a diagram on a test to refer to, and then sometimes I don't, right? Because if the diagram gives away everything, then that's not what I want. You know, like if I'm asking you to find the volume of a sphere, but I don't want you to know it's a sphere, then I'm defeating my own purpose if I give you a nice picture of a sphere on the test. All right? But in this case, I'd be more inclined to give it, because once you get, first off, you can see that we have z values of 1 and -1. These two are at the same level, at the same z level. So what's true for one is probably true for the other. It's just a question of whether this 0, 0, 1 was a maximum or a saddle point. All right? So what's happening is, I mean, we can't see up in the nether regions there, but if we could, we would see that this point has values of z that are both higher than it and lower than it. All right, so there's a transition that does not allow for it to be the highest point, to be the king of its particular hill. Question?
They're both local minutes?
They're both local minutes, yeah, because we have two legs here. So this one is the local min on this side, and the other one is the local min on the other side.
The first two I parts of it, it's asking us to take this, find local min and max, asking us to do it with f of the double derivative of x. Would we do that for y as well? If we did not that our x to the power 4 is also our y to the power 4.
For which part?
See how we find our local min and max? We put
The
it into
rules,
the
number
f,
1 and
x,
2.
x.
Oh, you're talking about these bad
What
boys.
do we do with y?
We don't bother with the
The
second order partial with respect to y.
Okay.
Yeah. We only look at it with respect to x. All right, so I'll put a star on number 7. That's actually a pretty tricky one. It does, I guess it doesn't have to be, but it requires a different way of thinking about it. So if you struggle with that one, I understand. I'll definitely take some time and go over that on Thursday. That's what I'll do. So, shortest distance to the plane requires you to use the distance formula. Now it's 3 variables, so we're talking x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared. All right. So we have our plane of x plus 2y plus z equals 4 and our coordinate. All right. So what we have to do is define this in such a way that we're finding the distance between any point on the plane and that particular coordinate. So what we'll do is we'll call a point on the plane, any point that we want, it doesn't really matter. We're going to call that point x, y, z. All right. We're going to call it that because that's what it is. All right. So what I would say is x minus 1 squared plus y minus 0 squared plus z plus 2 squared. All right. And so what we want to do here is use our knowledge of partial derivatives to figure out what the minimum distance would be between these 2 points. All right. So that understood point that's on the plane, x, y, z, that we really haven't defined yet, and that point in space. Now, we learned a technique in the last unit using vector relationships to help us find the distance. It involved projections and things like that. But what we're going to do is use the second derivative test as an alternative method. But if you really think about it, just going back to the last example, we were working with a function of x, a function in terms of x and y, not a function in terms of x, y, and z. So we have to make an adjustment. The good news is we have a relationship between x, y, and z. X plus 2y plus z is equal to 4, which means that z is equal to 4 minus x minus 2y. So I could redefine my function as x minus 1 squared plus, I'll clean the middle part up to y squared, which I think is a reasonable thing to do. And then I'm going to replace the z here with what z is equal to. And this ties back into the last unit in a nice way, because when we were finding the distance between planes, we had a point in space, and I said that you needed to come up with a point that's on the plane. And the way that we came up with the point on the plane was to determine on our own, decide. You know, you just pick. I want x to be equal to this. I want y to be equal to that. And then use the equation of the plane to determine what z has to be. Right? So you had control over x, you had control over y, but then z had to be something to satisfy the equation. And it came up on the last unit test also. That's what's happening here. I'm letting x be whatever it wants to be, y can be whatever it wants to be, but z has to follow this relationship. Right? Whatever x and y are, they have to be plugged in here to give us a particular z. Right? So when I replace the z with 4 minus x minus 2y, I get a new quantity of 6 minus x minus 2y, quantity squared. All right, so that's my function of x comma y. All right, and that's what I mean when I say I'm going to just get you started on this, because this is what you're going to find the partials. You're going to find partial with respect to x, partial with respect to y. You'll need your second order partials and your mixed, and apply second derivative test. And once you do that, you'll come up with an ordered pair that gives you, you might come up with more than one critical value. That's the thing to keep in mind. If you do, you need to flesh out which ones give you the minimum and which ones give you the maximum. Now, it wouldn't necessarily, I don't think anyway, make sense for this to return a maximum, because if it did, I mean, you're really thinking about a line going from a point in space to any point along a plane. There would be no maximum, because the highest would be an infinite distance. All right, but the shortest should be the straight line distance, the orthogonal vector between the plane and the point in space. All right, so you got your work cut out for you, but like I said, we'll start off next class with the continuation on this problem. All right, a nice little additional component to this is the idea that we could say, because distance d is equal to that whole square root radical, but we could also say that d squared, let me just, I want to bring it in a little bit more. D squared is equal to x minus 1 squared plus y squared plus all that stuff. The 6 minus x minus 2y squared. The reason that's a beneficial move is because we're still looking at a function of two variables. So what we can do is define this as f of x comma y. Well, I already used f of x comma y, so I'll call it g of x comma y. So the alternative to working with the whole radical and dealing with chain rule, or massive chain rule within chain rule, and finding all of these quantities, would be that I could determine the partials related to this function and not have to deal with all that mess. Right? So what I can do then is find the partial of g with respect to x. So in that case, we'd be looking at 2 times x minus 1 plus 2 times, let me just move that up, 6 minus x minus 2y to the first power times -1 on the inside, because again, it's with respect to x. All right, so I could do a little housekeeping here. 2x minus 2. I'm going to run through with a -1 and a 2 simultaneously. Keep an eye on this because, yeah, it's ordinarily something will screw up. So we're looking at plus 2x plus 4y. All right, we got some like terms. Nothing too crazy, but you know, it's worth it. Worth looking into here. So we have 4x plus 4y minus 14. All right, at some point along the lines, we're going to have to figure out the second order partial with respect to x. And by the way, there's nothing wrong with taking the derivative using this. But if the idea is that we're looking for the shortest distance between a point and a plane, we could find the shortest squared distance between the point and the plane, and that would correspond to the distance itself. Right? So we can get our critical values, but we could also get our second order partial right away. So I'll write it as g sub xx. Spare the notation, we get a 4 out of that. All right.
I'm sorry, does that mean we have to square it at the end?
No, because once we get our solution, it's telling us the x, y, and z values that minimize the squared distance from the point to the plane, which would in turn minimize the distance itself. So it amounts to the same thing. So if I wanted the actual distance, then I'd have to go plug it back into the original distance formula, but I don't need to do it in order to find the particular x and y values. So I can still minimize the squared value of the distance and get what I need from that. It makes life a little easier. A lot easier. Especially if you try taking the derivative of that thing. It's fun. Math fun. It's not. It's not fun at all. Not even math fun. First order partial with respect to y, we get 2y plus a lot of the same stuff, 2 times 6 minus x minus 2y, this time times -2. So we're looking at 2y, so that's going to be minus 24, then plus 4x plus 8y. So 10y plus 4x minus 24, barring anything too catastrophic. All right, so my second order partial with respect to y, so g sub yy is going to be 10. Now I do need the mixed second order partials, but that's not terrible in either case, because I could do it here. I could find g sub xy, in which case I get a 4. Or I can do it down here and find g sub yx, which is the same thing, because it's continuous. They're continuous functions. We're not looking at anything along the way here that gives us a thought that maybe there's something undefined or imaginary. So there's no reason to think g sub yx should be any different. As it turns out, it's exactly the same. All right, so it's not a proof, but it's further justification of something that we're taking as a truth. All right, so we have that information. So that's good. We got some good stuff here.
Professor, question. We're on page 75, question 7, right?
Yeah.
So
that's a good start.
Yeah. So I thought it was
this is going so well.
1 and -2. Where did the -1 come from?
The 1 and the -2. The 1 comes from the derivative with respect to x of the expression on the inside.
Oh, okay.
So ignore this, ignore that, because we treat them as constant.
Yeah.
Derivative of that, and this one, ignore this and that.
Give a -2.
Differentiate that.
Okay.
No, it's always a good idea to make sure you're looking at the right problem. Sorry.
No, I was just the squared thing still bothers me. I just can't process it.
So 3 is bigger than 2, right?
Yeah.
Okay. Is 3 squared bigger than 2 squared?
Yeah.
That's the idea.
What does that have to do with the distance formula, though?
It's a squared distance. It's a squared quantity. So if I'm telling you that I'm taking a distance and squaring that distance, its size relationship would remain the same. So if I minimize the squared distance, then I'm going to also minimize the distance itself. All right. So what that's saying is that if I tell you that Charlie ran 1 mile and Chris ran 30 miles, you know what the size relationship is. Now, if I tell you that, okay, square Charlie's distance and square whoever the other guy's distance, I forgot his name already, the size relationship is still going to be the same. If I minimize one distance and I minimize the other, the size distance will still remain the same. So if I have 2 quantities that are already squared values, if I minimize them both, then whatever ends up being smaller is still going to be smaller when you take the square root of it, right? So if I shrink down those 2 distances, if I go shrinky-dink style, if I take 2 objects and shrink them down to 1/8 of their size, so I'm going mini-me actually, what the relationship is between the square root of those values is still going to be the same as the relationship between the heights themselves.
So you said that like the size relationship means, you mean like just that literally
One's
like,
bigger than the other.
No,
Not
okay.
proportionality, because that's a different story. Because areas
what I
and size
understood.
are not necessarily in proportion, right? So, but what I'm talking about here is if you minimize one, then you're therefore minimizing the other.
Because see, I thought we were looking for exact values for partial derivatives, but then I understood proportionality for the partial derivatives, so I guess I'm just not understanding it.
It doesn't have to be proportional. It just has to be the fact that as you minimize, if I get the smallest distance that satisfies this equation, the x values that give the smallest values for this equation, then it would necessarily correspond to the distance formula itself.
So long as it works with the distance formula. We wouldn't get the exact same answer if we had the square root there and then we took the partial derivative. But we don't
You wouldn't
want
get the
that.
same partial derivatives, but you still get the same x and y values. You'd still get the same values to satisfy, or at least you'll still get
To
the
satisfy the
same,
equation.
yeah, to satisfy and get you the same minimum distance.
Okay. We don't need those exact values. We just want something that
Ultimately gets us the minimum distance. That's all we need.
isn't there one minimum distance?
Yeah.
So it's the same minimum distance.
It's going to be the same minimum distance, because if I minimize this equation, I'm going to be minimizing its square root also.
So then those partial derivatives are the same as if we left the square root, if we took the partial derivative with the square root?
Not necessarily. It's just that they will lead to a distance that is at a minimum,
Okay.
and so will these.
Okay.
For the bottom one, where did the GYX score come from?
Oh, just took the derivative of this bad boy with respect to x. So this and this go away, differentiate only this one. All right. Now, ultimately, we did not need that one because in our discriminant formula, it just asks for g sub xy, but it's just furthering the idea that if you find one mixed second order partial, as long as it's a continuous function, you've really found both of them. All right, so it doesn't matter. Okay. So let me just get the rule so I can point to. Actually, I have to minimize it. I was going to snip it and bring it down and then offer a typo bonus for not having it on the page, but it was there to begin with. So just to refresh, we need critical values, so we'll get that in a sec. But we also need the discriminant. The discriminant is pretty straightforward. You're just multiplying your second order partials and subtracting the square of the second order mixed partial, right? So it's calculation. But then once we do that, we have some work ahead of us.
If we only have constants in our second, oh, never mind, we have the first, no, we have to go through the first one. I just read those as the fxx and fyy. I was like, because we only have constants in our second derivative, so like, how can they be 0?
Oh, okay. Gotcha. So let's tackle our critical values. So set them equal to 0. 0 equals 4x plus 4y minus 14. Oh. Get out of there. All right. And then the other one, same deal. 0 equals 10y plus 4x minus 24. All right? They both have to be equal to each other, and they both have to be equal to 0. We've established the fact that they're both equal to 0. Now I have to let them both be equal to each other. So substitution is the way to go here because we have two equations with two variables. It's up to you which way you want to go. System of equations with two variables is not insanely difficult to handle. This one, it depends on the approach that you want to take, but,
X equals?
well,
Subtraction.
yeah, I was going to subtract and write it as 4x plus 4y equals 14, and then 4x plus 10y equals 24, and just subtract the second equation from the first one. It's pretty straightforward when you do that. You're also welcome to use reduced row echelon form in your calculators.
So make a matrix of those three.
A 2 by 3 matrix. Yeah.
Reduce, and then our augmented 1424 is our answer.
Yeah, you'll have it. It's pretty straightforward in that case. The only reason I'm not even defaulting to that at this moment, because normally, I mean, you know how I am with the calculator. I like going to that wherever possible. But, I mean, the 4s are going to cancel out nicely. I mean, it's going to be so clean. So 4 minus 10 is going to give me a negative 6y. And then we have a negative 10, right? So 5/3. All right, and so, I mean, the only drawback is we have to deal with some fractions, but it's not terrible because we're looking at, you plug it in here, for example. Actually, you might even consider knocking out the 4 off the bat, make this x plus y equals 7/2. Because then you're saying 7/2 minus 5/3. So 42/6 minus 10/6, so 32/6, oh geez. 16, is it 16/3?
Oh, 11/6.
11/6, I'm not even close.
Yeah.
Huh.
Oh, yeah, I got it after divided by 4.
11/6.
Yeah.
Should have gone to reduced row echelon form. All right, so these are my critical values. All right, so we already took care of that part. So that's good news. Now we just have to evaluate our equations. All right, so again,
But I was wondering, like she said, those are all constants, so,
It doesn't matter what the value you had then based on our formula.
right?
It
But there's
will
nowhere to
always
plug our
be-
constants because our partial derivatives are all constants.
second order partials are constant?
All
Right.
of our derivatives are.
4,
all of our
10,
second
4.
orders, yeah.
Oh, wonderful.
So why do we do that?
They're never gonna change.
Well, we need a critical value there
Wait, do we need our critical values though?
for life.
Not this problem, but what?
You just minimize it just by looking at the formula. And the
They're
values
critical.
that get closest to
You know, flex is 8th grade math on
the
your
square root.
All right, so XXYY minus or plus? I forget. Minus. Okay, so I didn't forget. 4 squared. So it's an even 0.
Wait, what?
24.
Not 4 squared?
No,
man?
4 times a 10. Not a
Oh, 4 times 10. Ah. Well, that's good because 0 would have been a disaster. 24?
Distance.
It would have meant that it's inconclusive, which would have sucked.
So what does that 24 mean though? Because that you're saying that it was supposed to be that minimum distance is supposed to be the same.
No, it just means
Oh,
that.
oh,
it goes to
that,
to
okay.
be-
My knowledge.
So we have these two possibilities. At least we know it's not a saddle point. We know that we can draw a conclusion. Now it's a question of, is it a local min or a local max? Since we're looking for the shortest distance between 2 points, I need it to be a local
It's a local minimum.
min. And that happens to be the case because my second order partial with respect to x is positive, thank the maker.
But what I don't understand is that we could have picked literally any value. We could have done 11 and 5, forget the division. And according to our formula, we still would have had a local minimum at 11 and 5 because there's no variables involved in either our determinant formula or our check against the...
This is just giving us a sense of rates of change from different directions and the rate of change of the rate of change from different directions. Around any location within the function, when nothing occurs unless you have a critical value. So it's kind of like saying, all right, I know that, yeah, my function decreases and it increases. Just going back to Calc 1. That's all well and good, but if you don't know where that critical value is, then you don't have a sense of where the minimum is, right? What's happening here is that there is a very large sweeping region for which this function is decreasing. And it's, well, actually we're looking to minimize, yeah, so decreasing, right? And so it's a question of where specifically will it hit its lowest point. That critical value is the driving force behind all of this because none of this is even relevant unless that's the case. So it's kind of like, and I write it as short handy as I can, but it's really, if this condition is satisfied, then define the discriminant, D, and all that good stuff. Because none of this happens without that. The converse is not true, right? It isn't a matter of do all this stuff and you've identified everything that you need to identify in terms of extrema. This has to happen first in order to identify whether or not there is an extreme value to begin with. Once you've done that, then all of this comes into play. But this is the part 2 that only happens after this condition has been satisfied. All right, so it really doesn't even, this is completely irrelevant if this doesn't have a satisfactory conclusion. All right, and so there's more to it than that, proof-wise, but that's the essence of it. One thing cannot happen without the other. It's not like these two things happen in conjunction where one can override the other. The second condition or set of conditions happen only after the first one has been satisfied. All right, so whether there's constants in there or variable quantities, it doesn't make a difference. It all has to do with whether or not there are critical values. All right, so anyway, we have our critical values, 11/6 and 5/3, and we've just established that it is in a region in which there is a minimum. All right, so we're talking a relative min at, I already forgot, 11/6, 5/3, so it's G of 11/6, comma 5/3.
So are the actual coordinates still those, or is it the square root of those?
Once we plug it in, oh, this will actually end up being the actual coordinates only because the components that make up my squared function
Yeah.
and the original function are essentially the same.
So would we have gotten the same thing if we did partial derivatives with the square root and everything? We would
Not
have the exact
necessarily.
same critical points?
Oh, with the critical points,
Because you're saying that's where the relative minimum is,
right, yeah, we would have got that, but we would have gotten different partials.
which doesn't really,
They would have cleaned up eventually to give us these solutions.
okay. And we can only do that with the distance formula.
Would they have given us?
Correct, if I understand what you're asking, yeah.
Would they have given us the same discriminant, or would they have cleaned up nicely but not into that 24 specifically?
They would have cleaned up nicely. I don't know that they would have given you the same discriminant because,
It just matters when it is, right? Not what it is.
yeah, because you would have had because it only would have it would have only started to clean up to equivalence once you set it equal to 0. This would have still been pretty nasty. Yeah.
And I'm sorry, what is our discriminant?
Our discriminant was this, 24.
That's not our that's not the distance.
No.
Okay.
So we're looking at 11 over 6 minus 1 squared plus 5/3 squared plus now it's really, I mean, I wrote it as g of 11 over 6 comma 5/3, but ultimately when I plug it into g of x comma y, I'm just plugging in the x and y values. This is actually if I want to know the real coordinates, right? So along this particular function, which does not seem to be overly useful. Uh, 11 over 6 5/3 squared. And I wrote it, I should have wrote it as 11 6 5/3. All right, so a little computation. What do you get?
For
25 over 6, even? All right, so that's equal to d squared. So d would be equal to 5 over root 6. And ultimately, that's what they were asking for, right? They said shortest. No. Not after like algebra 2.